Thank you. I'm going to talk about physical intelligence and essentially our journey over the last year and a half. So this is actually the first video that we publicly put out. It really, I think, kind of imbues what we care about, which is robots that are doing very dexterous tasks, useful tasks, and that feel sort of intelligent, that they come around and through perception of the world are able to manipulate these complicated things. Now, at a year, this is where we were, and what we really care about is general purpose robots doing general purpose tasks in the real world. So in this video, this robot has never seen this environment, has no data of this environment. My co-founder Chelsea is just giving it commands to do throughout the place to do something useful. So first it's close the counter, or close the cabinet, and then put the bowls and plates into the sink, and then it's going to be wipe up the spill. And what's really important here is, again, this has never been before seen, so what it has to be able to do is understand from its experience how to connect what a cabinet is, how does the cabinet move, how to clean up a spill, how to identify what part is the spill, that it needs to use the sponge to be able to do this, to be able to wipe that off. And I think a lot of my talk is going to be building towards how we can build general purpose robots to do this. And again, to hammer and hone, really our goal is to be as general as possible. So right now we collect data over a number of robotic platforms, single arm, more industrial type arms to mobile manipulators. But at the end, I'll kind of give a view of the future of where we expect things to be, where it's really any type of robot, anything that perceives the world and puts some action out, we should be able to imbue with some intelligence. And we want to be able to do tasks where right now we're focusing on home tasks because they're very general, we understand them well, we know there's a lot of diversity in the world, but it's not just limited to this, it's industrial tasks, it's really anything that's useful in the physical world. Now, this is kind of an overview of where I'll go. First, I'll talk about what's missing within robotics, what's difficult, what do we need to solve. Then, what capabilities have we in our first, a year and a half, what have we been able to learn? How can we generalize to new environments, new scenes, new tasks? And then finally, ways that you can try it out yourself. In particular, we've open sourced some models. So these videos are about 5 years old, and you see this very complicated things that these robots are able to do. They're able to do parkour. Some of the things that it's doing are things that I would have trouble doing. Maybe not this part. I could probably do that, but a lot of them are. I think at some point I might even do a backflip. I certainly can't do this. So what's missing from there? And then we put it into these industrial tasks, and they're able to do really quickly, very repetitive motions. This is providing real value right now. But the problem is once you take these same algorithms, you put them in the real world into a complicated setting, and here they even have QR codes to be able to identify things quickly go wrong. The number of ways in which mistakes can be made in the real world is extremely high. It's this combinatorial space of potential just disasters. You need to understand where to place the object, how to do it, but also understand its own dynamics, the dynamics of these trays you're placing it on top. And I think this video actually got cut off a little bit, but the robot eventually falls down. So we really need to be able to understand all of this and be safe within it. But people can do really complicated, really impressive feats of strength. We can also use tools to be able to accomplish tasks. We can do it with really fine manipulation. We can handle keyboards, which is also an extremely dexterous task. Finally, we can even operate machines. So a car is this complicated machine. You can just get in it and understand how to do it. You can understand how to operate a bicycle, for instance. I think this is very impressive about people. But now if we look at robots, this video is actually since 2008, so 17 years old. And what you see is a robot actually able to do some really complicated tasks. Now, the missing piece here compared to all the other autonomous robots that I showed earlier is that this is human teleoperated. So from this, I feel like it can mop the floor and vacuum and clean up after you. What's really missing in this case, the thing that came in and imbued it with the ability to do this was intelligence. So all of what we care about at Pi, at Physical Intelligence, is this intelligence. How do we make these things actually work in the real world? And it feels like if hardware from 2008 could do these complicated tasks, maybe hardware isn't the big bottleneck, it's really this intelligence. So if we take a step back and say, well, what's the closest to this kind of artificial intelligence today? It's really foundation models. And if we look at the progress over the last 5 years, we see pretty much every benchmark that's created, it goes up and to the right pretty quickly. Each successive one gets solved more and more quickly. Some of the early ones took 3 years. Now you have a task like humanities last exam, and it's just like a massive jump, just month over month. It feels like everything that gets put into these works really well and is able to be solved. You also have things like IMO Gold, so they're able to solve math problems, and I think recently some computer science competitions better than any of the participating teams, and these people are kind of best in the world at these tasks. We can even do these like video generations that are extremely complex. They feel like physical understanding. Like surely the motions at least seem reasonable. So a lot of the question here is kind of what's missing within robotics? Why isn't robotics making this kind of up and to the right movement? And really, I think if we thought about it, it would be this like flat line at the bottom here if we had any like real complicated tasks. So there's a couple reasons why. One, and this is kind of a fancy way of saying that robotics is just really hard. It's essentially, when you think about the dexterity that goes into these tasks, it's something that we've evolved over millions and millions of years to be able to do. I mean, even animals who are comparatively much less intelligent can do these really dexterous tasks. But things like playing chess were actually pretty easy for AI to solve. That's what really gets to the core of this Moravec's paradox. I think a task that I think about a lot is like opening a tea bag and making tea. You have to understand how much friction do I need to apply to be able to tear that tea bag. Once I tear the tea bag, where is the bag within the outer shell? Where's the cable, or where's the like string within it, the tag? It's basically, as you go deeper and deeper into this, you realize there's just so many layers of complexity, and just dexterity is really difficult. Another thing that's missing is just data. So this was, in 2004, the largest robotics data set that was open source. It was about 4,000 hours, which is about half a year worth of data. It was like every open source one combined into one, including some pretty large data sets we collected at Google. If you look at GPT-2, from many years before that, it's just, I guess, 2 orders of magnitude larger. Llama 3, significantly larger than that. So clearly a big thing that we're missing is data. But there's also a lot on the algorithm side. So the biggest breakthroughs I think we've had in terms of the ability to ingest heterogeneous data and train robots to be able to do complicated things comes basically on the backbones of vision language models, where you take a vision language model which takes in some image, some prompt of what to do, and outputs a response. If we just switch this out for actions instead, so movements of the robot arms, it turns out we can inherit a lot from these. We can start to do complicated tasks, like understand what these new objects are. I think that the way that I really think about this is by putting enough of this data in there and representing the actions in the right way, you can get the VLM to speak robot, to speak something that the robot can understand, and we know we can kind of translate concepts through different languages. We can do something very similar for robotics. And this has been a big breakthrough for how we can handle the generalization and capabilities of robots. So I want to start with just with capabilities, and the first 6 months or so of Pi, our whole goal was to kind of prove to ourselves that we can learn these complicated tasks that you hadn't seen before, that are hard to simulate, that are hard to code up in some sort of structured way. So we started with this large open source data set that wasn't large by I think today's standards, but at the time. And then we collected a lot of data through teleoperation. So we set up a really nice teleoperation setup, and we have people doing things like folding shirts, which you just saw Dinah's got a lot of data of folding shirts. And we turned this into a number of different tasks. I think here is about 100 tasks. It's around 10,000 hours, so a little bit over a year. Tasks as complicated as like folding a box to diverse laundry and more. And we see a lot of variation over the visuals in this, over the movements across it. And we basically want to see with that much data, what can we accomplish? The other thing we did was work on the underlying model. And one thing that we've learned within robotics is, compared to VLM tasks where we can discretize tokens that represent language very well, a lot of actions within robotics are continuous, and thus we should use a representation better for continuous actions. So we have this action expert, which is essentially, to a rough approximation, think of it as like a diffusion model attached onto the weights of this VLM backbone. It takes in an image, a prompt, and then learns to output these continuous actions. So with this, we could do a number of tasks, from building that box that I showed, to picking up eggs and putting them into an egg carton, to folding laundry and then to busing a table. And in this case, I think with this table busing, we specifically chose objects that it's never seen before that were kind of weird. We just went to a party supply store and tried to show, really at the end of the day, it understands what these objects are, where these objects go. These are things that it can inherit from the VLM. I think if you look at this like box building too, it's a really like complicated multi-stage task where you think it's not making that much progress throughout the task, and then suddenly the box is built. As I watch it, I think it's hard, and I think it took us about a month to figure out how to even teleoperate how to do this, and now the robot does it better than we do, better than a human teleoperator would be able to do it. We also had some emergent abilities that we didn't necessarily intend to collect data for. We certainly wouldn't have coded up, but here it's actually picked up two shirts, and it just picks one out, pulls them apart, and puts it back in. These are the kind of things that through machine learning and through large-scale models we can actually ingest and suddenly be able to handle. This is the type of generalization that we really care about, that if I go to some new environment, I'm going to see scenes like this that we couldn't have gone out of our way to collect, but hopefully happen, and then it learns to still spread out the shirt and go in and fold it. So if we keep watching it, we'll eventually succeed at getting it to a flat enough state, and then once it's in that state, this is something that there is a fair amount of data on, so it's really about having it be robust enough to get to these kind of states that it's seen before. We also were able to have a policy. This policy, I think, takes about 10 minutes to fully roll out. It's all a single model that's outputting actions for both arms, for the mobile base, and it does something as complicated as get all the laundry, go through and fold it. You also see, as it goes, it is going to make some mistakes. I think one of the next shirts, it kind of starts not grasping it effectively. But one thing that we found is because we have enough diversity of data that covers states, we actually have robustness to this kind of mistake. Essentially, like from that state, it's seen something else like that, and it knows what to do to be able to correct it. At times, it means that like here, like the fold wasn't perfect, it can actually fix it and put it on here. Now, there's still a lot of room to go where like speed, for instance, is. Like this still took 10 minutes, and I think it probably would take me 3 minutes. I think there's a lot of work to do to fix this. But we're really seeing these signs that it can understand long horizon tasks, very complex tasks that are otherwise kind of impossible to simulate, to set up. Another one that I really like is this lighting a match and then lighting a candle. I think this is something that without dexterity is without tactile feedback is extremely hard. If you get rid of the tactile feedback from a person, they can figure out how to do it, but it takes them a lot longer. Basically, our normal grasps are not robust to not having tactile feedback. I think when I really like break down to why this is possible without this tactile information, I think a lot of it is that these cameras are essentially, there's a wrist camera on each arm. It's giving you some signal that's not unlike tactile information. It's local. It's actually about the exact same, the resolution of that camera is almost the same as the number of receptors in my hands. And we're able to, learn these complicated tasks. And this one, like the lighting match is like 95, 98%. So it like really can figure this out. We also can then take that model and fine tune it with data that we didn't collect, that other people collected and sent to us, send back a model, and it works fairly well. Here we have making coffee in a Keurig, and also like handling this this deformable scarf. And then finally, we can even generalize to new tasks that we hadn't seen before. So here's a number of different sandwiches, and what we did was just collect a variety of ways in which you can make a sandwich, roll it out, and in this case, a lot of the generalization comes through the high-level policy. There's a high-level policy that takes some long horizon command, like make me a ham and cheese sandwich, and breaks it down into sub-steps that the low-level policy can then accomplish. This is something where we can inherit a lot more information from the internet, because this is directly a task that like VLMs are going to have. And I think as much as we think about this, we think about how can we collect data, and then also what can we inherit from the internet that's already there. Okay, so the other part, and I think this last slide kind of nodded to this, is generalization. How do we do new tasks or generalize to new environments? First, it's worth kind of thinking about why is this really hard? And so I found a bunch of videos within our data of different cabinets. And if you look at each one, they're articulated in different ways. Some are high, some are low, some you need to pull, some have some like revolute joint. They have different mechanisms for actually grabbing it. Either it's like a hidden handle or a little knob. Some require you to pull it out and then re-grasp, move around. So there's there's really so much complexity in the world when you think about it, even in this like very complicated task. These are also a bunch of different sinks that we've navigated to in our data. Each one looks extremely different. I think you'd think it'd be very easy to kind of like write down, here are the rules of what a sink is, but when you see it in the context of the broader kitchen, it's actually very difficult, and really at the end of the day, what you need to do is inherit this web knowledge and then collect data across a variety of scenes to be able to generalize to the next one. The other thing that we do is, as I said, collect a lot of diverse data. So first, data of this mobile platform. In this case, for all these results I'm going to show, we had 400 hours of data of this, which is actually like not in the scheme of things very much. It's less than a month worth of data. But we also threw in a bunch of web data, whether it's bounding boxes, VQA questions, semantic segmentation, and then different robots in different environments and different robots within our lab setting doing a variety of tasks. And what we found is that each one of these data sets actually is extremely important, some because it's easier to collect, some because we can see more environments with it, but each of them is actually able to transfer to our ability on a just mobile manipulator. So starting back at Pi 0, where we had 10,000 hours of data, we then scaled it up to well over 10,000 hours to around 1,000 tasks collected and around 100 environments. And so we wanted to look at is what can we learn when we do this? One thing that we can do is, and yeah, this is the same. This is just a demonstration of what this data looks like. Some of it is like nightstand tasks. We saw some of this like wiping spills, a messy bedroom. Really, the diversity that you see when you go out into the real world, in our case, to Airbnbs throughout the world, you see a lot of diversity. We also came up with a new model design because our previous model, though fairly expressive, was very slow to train. Concretely, what we did was we added in a discrete representation of actions along with our continuous representation of actions. Now, this discrete representation makes it much faster to learn. Essentially, the training signal from this cross-entropy loss is much better, but inference is still really fast. It's still 100 milliseconds, and it turns out through this whole process, we can ingest a lot more and understand a lot more from web data. So looking at what it looks like to scale with environments, first I want to talk about broader pre-training. So we collected data on multiple environments, on multiple different robots, and we trained with all this. If I collect, in this case, like 100 hours in this scene, a fair amount in these specific scenes, without pre-training, we get to about 40% performance, so still not very good. But with this pre-training, this data that makes the policy a lot more robust, essentially, and understand the world better, again, no other mobile manipulator data, just mobile manipulation from this scene, we essentially double performance. So the next thing we wanted to see is, what if we remove the data from this environment and only look at unseen environments? So we went and first collected in 3 different scenes, and these are 3 images from those first Airbnbs that we collected in. And you see the performance is still pretty bad. It's worse than without pre-training even. If I then scale it up and we do 22 locations, we're actually already better than in-distribution data without pre-training. We still have this kind of like high watermark of in-distribution with pre-training, but we're able to catch up a fair amount. And then as we got to about 100 locations, and I think one thing that was really important here is we didn't know if this was going to be 10, 100, 1,000, 10,000. We don't have scaling laws within robotics. We don't have these like clear scales that say, okay, at this point, if I increase compute or I increase data this much, I'm going to be able to do this. So we weren't really sure where we would kind of cross this threshold, but it turned out around 100, which is fairly collectible, we could match this in-distribution performance. Now, I think there's still a lot of open questions of, what if I scale well beyond that? Can I actually exceed this in-distribution performance? Clearly within like the language model world, having this web scale data allows you to beat this in-distribution performance, but that's kind of yet to be seen. The other thing is how much it matters that we had this pre-training data set with all the action data of different robots. For out-of-distribution performance, it's essential. Without it, we basically like dropped all the performance. It does nothing. It's like not robust. It's not able to make sense of that world. So it's really important, first starting with a VLM backbone and then adding in this diverse pre-training data set. Now, with that, we're able to do tasks like this. I showed one at the start. In this case, we don't even say, break it down into these steps. Just clean the bedroom, and it's able to understand this is the laundry, this is where the bed is, this is some trash on the ground, the trash goes in the trash can, the laundry goes in the laundry hamper, and what a unmade bed looks like. I think this is actually like a really complicated task that we don't realize. Sheets look the same color. What is a flat sheet? What is like a when am I done with this task? Where should I put the pillow? These are just like a lot more complicated than I thought they might be. So we ran a lot of these just for 10 plus minutes and just to kind of see what would happen. At times we were giving it commands and seeing how it would respond to this. And essentially in all these scenes, other than the fact that the robot embodiment maybe has some constraints that it needs to move in a certain direction, it's actually able to do pretty complicated tasks. This one here where it's putting items in the sink is not something that's in the train data at all. So there's putting items in the sink from right next to it, but not navigating somewhere, picking it up, and bringing it back. These will go on for way too long if I let them, so I will move on. So another thing that we're thinking about is how can we have kind of like impact for the broader robotics community? How can we forward this community? And so one thing we've done is open source our models. Now, they're really easy to use. You can essentially just go and download them. We have each of the models that we've published is out there now, and some of which, they're easy to call. You essentially just like tell it the observations that are coming in, the action space, and it's able to output actions for you. Some of them work zero shot, especially if you have robots that we collected in. Otherwise, we have fine-tuning APIs where people can try them out. And this was about 3 weeks ago, and actually within the first day, people tried it. One person with fine-tuning and a few people with zero shot. There's this like, one person tried napkin folding, which I don't think we have data of actual napkin folding. We may have towels and shirts, but we don't have any napkin folding data. And I guess was able to do it 25 in a row, which is a little surprising to me, but exciting. Some other people said clean up the table with kind of these unseen ones, and this is part of a video of this. They say this, and immediately it starts outputting actions that moves this. I'm not sure where the camera placement is, because we didn't like ask them to put the camera in a specific location. We didn't actually collect much data on this robot. This is probably our least represented robot in our overall data mixture. On the left, somebody trained it to just pick up a ball on a completely unseen robot to us. And without this, it was essentially zero performance. And with Pi 0.5, they're able to get it to a pretty high success rate. So now I kind of want to just paint a brief picture of what I think is next. And I think putting some like sobriety on all this, we're still a bit away from these things really working in useful ways in the real world. I think this is still a very like fundamental research problem. We're not like 3 months away as much as we're able to go into a new home and do something. It needs to be a little bit more robust, faster. I think we understand that performance is a big issue here, that safety is a big issue if we're able to put these things in the real world and actually do something particularly useful. But if we're able to get to a point where we can actually just imbue intelligence to these, I think it's kind of exciting to think of what we can do. First, I saw this on Twitter recently. This is just all the humanoid companies that are out there right now. They had like 80 of them in this Figma. And it would be great to be at a point where we actually understand the physical embodiment of each one, whether we have data in it or not. We can essentially imbue intelligence to each of these. And now, right now, we do this through partner data, where they send us data and we send them a model back. And we're able to see that we have pretty big gains by having this pre-training mixture, and we're making progress on this. We're not quite at this point of like where language models are, where it's zero shot and you give it some new task it's never seen before and understands it, but we're making a lot of progress. But I think it's also important to think beyond just like the humanoid embodiment. You know, there's things like robot vacuums that are working well in the world that are making sense of a spill, in this case, just to drive over it. But there's also ones doing kind of industrial tasks that this is all data and embodiments of robots, but also more complicated things, or maybe not more complicated, more different than how robots are currently used. We can do drones. We make no assumptions of this in our data. We're focused particularly on dexterous manipulation data because we think this is the hardest problem. And if we solve that, we can also solve these. But it's really, at the end of the day, there's images coming in and there's actions coming out. We can also do things like surgery, potentially. I think there's a few papers on how you can learn to do this, but this is an area that is completely on limits for these types of models. Farming and agriculture, also kind of like weirder robots. Like this one in the bottom right has 21 cameras and a bunch of different joints. Again, each of these is controlled not through our models at this time, but I think it's really useful to start thinking, if we think outside the box, what can we actually accomplish? And what can you breathe intelligence into? Now, finally, Stanford had this report on essentially the broader field of AI, and one thing that I saw, and there's a few papers on this, is when are we expecting to run out of data on the web or data that we can train from? And people estimated around 300 trillion tokens, and that if you extrapolate the curve and include growth of data, I think there's 30,000 hours per year of YouTube data, for instance, being put up. We'll run out of data to train on in 2028. Now, if I like cast that to seconds and then to years, this is 3.2 million years, which feels like a lot of time. But if you actually look, right now there's 5 million robots out in the world doing useful things. These are mostly industrial robots. They're not like out there doing general purpose things like we are. But you realize, like, even at this scale, which is maybe not that crazy, it takes 8 months to get that much data. If robots continue to grow and each person has their own personal robot, every 3 hours we collect enough data. And what's really nice is this is data in the real world doing something useful. There's not, you can't like make things up in the real world in the same way. It has to actually do something and be grounded in it. So this data is potentially of much higher quality. So I think there's a world in which robotics serves this future purpose of supplying the data for every foundation model, and eventually eclipses what everyone else has. So I think that's all I have. Essentially, our goal is to bring this general purpose AI that we've seen on the internet and web scale into the physical world. And I will take questions. So essentially, yeah, when do we need to fine tune versus not? Yeah, I think fine tuning is particularly useful if it's at this point, if it's some unseen embodiment, you almost certainly need some degree of fine tuning. If it's some unseen task that isn't that similar to what's in the pre-trained data set, you probably need it. I think even now, as was mentioned in Dinah's talk, we're starting to see with enough pre-trained data and with a capable enough pre-trained model, we're actually, before we would train it for a specific task to try to elicit even better performance, we now see the pre-trained model has about the same performance as a fine-tuned model on a specific task. So I don't think for those that we need to do it, but it's really when you're trying to imbue it with some new data or some new task. At the same time, ideally we include that in pre-training, and you actually then generalize it a little better. The pre-trained model still learns it quite well.
You talk about pre-training and your communication data scale. The LLMs have moved on now a bit to an RL age. Mm-hmm. So what's the RL story?
Yeah.
Like,
I think
online, like RL to solve tasks, what is your predictive story? Like, how do you think of this?
Yeah, so I mean, I think this is definitely like one of these big unsolved problems for us. Like, how do we get to performance and to faster speeds? And I think RL is probably the key to being able to do that. I would say so far, all these results are not focused on that because we really felt like the first thing we need to do is just, you need to start with this foundation and then you can start exploring. I think it's similar also with simulation data, human data, all these other things. You need to start with this foundation of robotics data to be able to make sure you're making progress in the right direction. But I think RL, at first it'll probably be offline RL to be able to just elicit the best performance out of the data that we have, and then eventually move to more online things that can improve past where maybe a human can even tally op.
The consumer applications look great. Are there any plans to look after industrial applications?
Yeah, I think, I mean, right now, again, the only reason why we've done more like consumer applications is because we have access to a variety. It's like, and we can go and rent an Airbnb, or you can come to my home and collect data. Several of my co-founders or homes are in this data set. So it's really about access more than anything. Like, we do have a number of tasks that are more industrial. We have some like assembly and plugging in cables tasks. And I think we will continue to expand the sort of breadth of these types of tasks. It just hasn't been the focus at first because what we cared about was just diversity. I also think there's something nice in even a single home, and the things that you do at a home are gonna end up being much more diverse than a single industrial job. So one could go and collect a ton of data of one task, so like a pick and place in a warehouse, and it's probably not gonna transfer that well to the rest of the tasks. Whereas if we start with the most broad range tasks that have the most environment generalization or diversity, then I think we can improve more on the other tasks.
You mentioned all these different data sources, right? Like online, like YouTube videos, Keynote, annotation, also just teleoperating websites, synthetic generated data simulations. How do you kind of see these different data sources contributing to formulating that like generalization?
Yeah.
Or I guess even like task requirements or something.
Yeah, I guess I maybe have two parts to my answer to this. One is just that I think first we really do need this like broad, dexterous robotics data to be able to start getting these types of transfer out of these tasks. I think like zero-shot transfer is much more difficult to get to work, and particularly for anything dexterous. Right now, where I see these things playing a role is really for semantic transfer, similar to how web data transfers. So if you record, like add in a bunch of YouTube data, you might be able to understand how to put together new tasks, but you're not gonna learn fundamentally new dexterous manipulations. Maybe in some like long run, we can start to extract these from it, but I think those are much more challenging. So it's really more about like the semantic understanding of the world than anything else.
Can you talk a little bit about your strategy on, do you try to learn everything end to end? You demonstrate the final task, meaning do you expect all the basic skills to just emerge, or do you go in and teach certain things, like localize, do this?
Yeah, pretty much everything we do is just end-to-end. So just try to do the full task. And I think there's some really nice things from that where you essentially get some robustness because you've done long horizon tasks where maybe even an operator while collecting data of it made a mistake and you have this like recovery for it. I would say if I look back 2 years ago to like at Google, some of the data we collected would be a pick task and you pick the object up and just hold it. If you miss, what happens is it makes the object and it holds the hand up with no object in it. Like it didn't learn that what it cared about was picking up the object. But if you do this much longer horizon collection where you're actually doing this useful task, you start to get these recovery behaviors and you result with a much more robust policy. I've been told we're out of time.